Einstein's thought style in all of this work always came back to certain characteristic ways of reasoning. He was a relativist and positivist, that is to say, somebody who thought that really we just want to base our ideas on what we can observe. But he was also an absolutist realist, somebody who really wanted to get to the bottom of things, who believed that there was an order of physical reality and that we could capture that reality, that we could make a map in our conceptual, imaginative physics world. We could map our representations onto the things that could be observed in a way that truly captured the way the world was divided. And to get at these different aspects of his interests, which he held simultaneously in many respects, he was constantly coming back to principles. What are the starting points of our physics? Where do we want to begin? The principle of relativity, that every frame is equivalent to every other constantly moving frame of reference, and that no one of them has a special or privileged existence. But it was also true that Einstein invoked the idea of heuristics, really for the first time in such a powerful way at the beginning of his work in 1905, when he introduces the one paper that he calls revolutionary, his photon paper. He says it's a heuristic because he knows he does not have a way of reconciling it with the theory of waves. It's only a starting point, an important one that captures an aspect of reality. It doesn't yet merit truly being considered to be a theory in a full sense, but it's an important step, and it captures a whole range of phenomena that previously had not been grasped. So you have principles that stand importantly for Einstein at the beginning. They aren't given to us in any certain way. They earn their keep by the consequences that we draw from them. And he has heuristics, which are sometimes like starting point principles, but they're provisional. They're a starting way of moving towards understanding phenomena, knowing that it'll only be in the future that we'll be able to reconcile these different ideas. And that's true of the photon. So the photon, Einstein knows, is incompatible as it stands with the wave theory of light, the most important 19th century development in all of physics. But Einstein trusts that in the future they'll be reconciled. It was almost 50 years later that that was so, but it was an important step forward. Einstein also invokes thought experiments. We've seen how he uses trains and lightning strikes, coordinating clocks in different stations, moving in an elevator. What kind of experiments could you do in an elevator that was accelerating, and how that might be indistinguishable from, say, doing an experiment in a laboratory within a gravitational field. Einstein was constantly invoking such thought experiments. Imagine a disk spinning. What happens to the circumference? What happens to the radius? Imagine the worker falling off of the roof and he sees his tools falling next to him as if there was no gravity. All of these thought experiments were ways of refining concepts, of establishing those principles that would earn their keep through the consequences to which they led. And then Einstein's papers always ended with some measurable prediction, or at least the major papers did. Brownian motion, special relativity, the photon, general relativity, all of these papers and many others besides them led to things that you could measure, to consequences for the world. So these are elements of Einstein's thought style, and they're as characteristic of his way of reasoning as the artistic style of a major painter might be. And we've encountered artistic style, or the anti-style of the Bauhaus, the style of anti-style, where they tried to extract forms out of the decorative to find a kind of aesthetic of functionality, an engineering-based aesthetic in some ways, or an aesthetically modified or modulated form of engineering. I think of Neurath's disdain for the electric light that was masquerading as a gas lamp or a chandelier that held candles. He hated that, and he loved the lamps that revealed their function. We talked about how the Vienna Circle, many of the leaders being mathematical physicists of different kinds, that they loved Einstein's criticism of space and time. They loved his criticism of what it meant for two events to be simultaneous. And they wanted that conceptual criticism, that honing of concepts down to that which could be understood clearly and given a kind of operational aspect. And they wanted that model, what simultaneity was for Einstein, to be the model for so many concepts in the social sciences and beyond. Einstein's own world pushed on this idea of completeness, externality, intelligibility. He was always wanting to extend these concepts, to take the idea of time and space, taking on Minkowski's idea of space-time, and then modulating that by Riemann's notion of curved space and time, so that the measure of distance, or space-time distance, would change depending on where the mass energy in the world was. And you began to be able to think about geometry as inseparable from physics. Geometry wasn't just a useful way of representing physical laws, that physical laws were embodied in geometry. And geometry was ultimately what determined how physics worked. For Einstein in general relativity, there's no force. Force simply drops out as a concept. The law of motion is really as simple as it could be. It's an object in motion follows a straight line. The rub is that a straight line is defined in a complicated way depending on where the mass energy of the world is, and that fixes the geometry, and then in the geometry you can find what the shortest line is, and then you can see how an object would move. General relativity soon folded into a crossover with war, pacifism, and internationalism. When Arthur Eddington mounted an expedition, we've discussed this again earlier in the course, to confirm Einstein's theory. And it was not just a random choice. Eddington was a pacifist, a friend, somebody who wanted the expedition that he conducted to check Einstein's theory as a way of creating a kind of conciliation among nations at the highest level of abstraction, at the core of the most advanced physics of the day. We see the connections between science and art and culture in other ways too. Erich Mendelssohn's Einstein Tower is both an instrument. The building itself is an instrument that draws in sunlight, passes it through a prism, and then we look to see if we can see a change in the frequency of certain spectral lines that would indicate that there really was a redshift, blue shift that corresponded to gravity, as Einstein put it. It was a difficult experiment. It didn't quite work out. But the tower was also a way of expressing in alliance with artistic movements. And Mendelssohn's Einstein Tower drew on the whole tradition of contemporary art at that time. Einstein himself, the figure of Einstein, came to stand in the Weimar period as a figure of modernity, to be put on display by Hannah Höch in her collage as a kind of symbol, as much as the technology of the day and some of the other figures of modernity, as somebody who stood for a criticism of that which was traditional. So even if Einstein is in certain ways trying to purify, to make classic in a certain way, an extension of the older physics, he's also seen as breaking with it, of offering a kind of new road forward for poets like William Carlos Williams and many others at the time, who saw Einstein's break with the absolute as authorizing their own way forward, whether it's Hannah Höch or William Carlos Williams or some of the architects. Buckminster Fuller comes to mind. People saw Einstein, his person and his work, as in a way sanctioning their concerns with breaking with an older form of classical formations in each of their own disciplines. Einstein, by 1929, was on the cover of Time magazine, just one instance of many times when he was on the cover of Time magazine, but already an indication before nuclear weapons, before he becomes a kind of figure that's associated with a new and dangerous world of technology. But already in the 1920s, Einstein stood as somebody who was a sign and symbol of this new age. painters like Dali took Einstein's theory and explored its consequences inside their work itself. Dali talked about the extravagant and solitary, paranoia, critical camembert of time and space. That idea of bending time and space, embodied in the melting clocks, became a theme for people all over the cultural map. At the same time, if general relativity offered material for philosophers to explore the meaning of space and time and whether this was a break from Kantianism or a reaffirmation of Kantianism, for painters, for architects, for the collage makers, or for people across poetry and literature, it was also, over the years, the source of new technologies. And if you think about our machines, the global positioning system of satellites that are embodied now in every phone, and missiles, satellite structures in mapping the world, in all sorts of new applications that are proliferating moment by moment as the cost of a GPS receiver goes more or less to zero, this becomes a technology that saturates the way we move along the streets. It's no longer an arcane technology that's only accessible to the wealthy or the military. It's something that's simply part of how we move about the world. But general relativity remains the source of physics and metaphysics. General relativity, as it's embodied in black holes, becomes the laboratory for some of the most advanced ideas about string theory, general relativity, about questions about what the nature of geometry ultimately will be. Will geometry not only be bent into non-Euclidean form, but also have a kind of derivative life? Will space and time be only rough approximations of other ideas that are even deeper? What is the dimensionality of the world? Does reality lie in 4 dimensions at all, or is that simply a kind of illusion? These are questions that are coming out of physics as it explores the collision of general relativity and quantum theory in the black hole, the conceptual and real laboratory where these two pillars of the 20th century collide most strikingly, and continues to provide some of the most interesting new ideas about physics and about the ideas that lie at the basis of physics. Nuclear weapons are another legacy of the 20th century, and we see bits and pieces of those weapons, although Einstein didn't in any fundamental way work on nuclear weapons in a direct way. He was considered to be a security risk, so they only would ask him very fragmentary questions from the Manhattan Project and were always fearful that he would guess what they were doing. Well, of course he knew what they were doing. But in the discovery moments of nuclear fission in 1939, Lise Meitner had recalled a lecture by Einstein about E equals mc squared and used that understanding to, for the first time, to really grasp what nuclear fission was about. She realized that as the uranium nucleus broke into pieces, that the masses of the pieces added up to less than the original mass of the uranium nucleus, and that difference was emerging as energy. There are other ways, too, of understanding nuclear fission that her cousin, for instance, put forward. But Meitner herself, who had done some of the most fundamental work on the experimental side of nuclear fission, was driven to a certain extent in her original understanding by her recollection of E equals mc squared. Einstein's involvement with the nuclear weapon had one other side, his profound fear of what the Nazis would do should they get the weapon first. And it was that drove him to ally himself with other physicists in alerting Franklin Roosevelt of that danger and arguing that Roosevelt should be alert to the possibility that might be afforded of making nuclear weapons during the war that was unfolding. Einstein finally was shaped by what he saw as the consequence of nuclear weapons. Once they existed, he felt a tremendous responsibility individually and as part of the larger community of physicists to help put some sense and rationality into the production and disposition and possible use of these weapons. He came more and more to fear that nuclear weapons could actually lead to the general annihilation of humankind, and the H-bomb could be a step along that path of perdition. Finally, we talked in this course about the quantum. Einstein grappling with these ideas of the discrete nature of the world very early on, in statistical form, in his Boltzmannian orientation about gases and Brownian motion and so on. But then more fundamentally, as he began to look at the discrete nature of light, and he began to talk about how photons were absorbed and emitted. In a way, Einstein was, as much as anyone, really the creator of the quantum world. He had doubts about it, he worried about it, but it was never because he didn't think that quantum reasoning was important or that quantum mechanics led to correct predictions. It was that he didn't see it as complete. He was constantly hoping that we could have a representation of the world that would map without residue onto the structure of phenomena themselves. That's what drove his arguments with Niels Bohr. That's what drove his invention of this thought experiment, the Einstein-Podolsky-Rosen. That's what really created his anxiety about the quantum theory, hoping that something like an extension of general relativity would actually capture the phenomena of the quantum world, and that you would have a complete understanding, or at least begin to glimpse a complete representation of a determined causal world out there. John Bell, about whom we've seen some important work in the previous lecture, was shaped by his encounter with Einsteinian world. He always thought that it was Einstein who had the better position than Niels Bohr did. But as he tried to figure out how to make a complete representation of the world, something like what Einstein might have wanted, he made his discovery of the Bell's inequality that came out of his reasoning about the Einstein-Podolsky-Rosen doubts, and created this test that others then took and actually performed that showed that there was going to be no complete theory of the quantum that would ignore the strange, spooky nature of entangled systems of, say, two electrons that are bound up together and then separated out. We look at one and we can know something about the other. That it creates one inseparable system in important ways, and that really there was going to be no hope that you could, as Einstein had dreamed, imagine a bubble around one of them and act as if everything was fixed within that small space-time bubble. That really a system could be quite extended and still entangled in this way. That's led, since the time of Bell in the 1990s and the 2000s, to a new form of technology where quantum cryptography, quantum computing, the kinds of things that we have seen explored by people like Misha Lukin and many others who are beginning to push this idea of the quantum entanglement into technology itself.